Welcome back to the Deep Dive. I'm glad you could join us again as we continue our series, Beyond Transformer, the next generation of sequence and language modeling. We've covered a lot of ground already, haven't we? We started by really looking hard at the transformer, its strengths, definitely, but also where it struggles, especially with those super long sequences and the quadratic scaling headache.
Right, that scaling issue is a big motivator for this whole field.
Exactly. Then we went back to the roots of state-space models, exploring HIPPO and how it laid the groundwork for continuous time memory, and then S4, which brought in structured matrices for efficiency.
And that led us to Mamba 1.
Yes, Mamba 1, a real breakthrough, the first SSM that could genuinely compete with transformers on language tasks. It was quite something.
It really was. And today we're diving into Mamba 2. And this isn't just, Mamba version 1.1.
Okay.
It's a significant refinement. Its core mission, really, is tackling a key limitation of Mamba 1 head-on. Its hardware efficiency, especially during that crucial large-scale training phase.
Ah, the training bottleneck we touched on before.
Precisely. So we're going to unpack two absolutely central ideas today: structured state space duality, or SSD, and this concept called the matrix mixer framework. And these aren't just like fancy academic terms. They represent a fundamental shift in how we think about these models. They enable faster algorithms, and this is really key. They let us borrow and adapt systems optimizations perfected for transformers, things essential for training huge models, and apply them directly to SSMs.
Okay, so bridging the gap between SSM theory and practical large-scale training. That sounds like the core focus.
Exactly. We aim for a deep, professional overview today, focusing on the core ideas and results from the source material, ensuring high knowledge transfer for you. No unnecessary tangents, just the essentials. #I, revisiting Mamba 1's success and its training bottleneck.
Okay, so before we jump fully into Mamba 2, let's quickly revisit Mamba 1. It was a major step, right? Showing an SSM could match, sometimes even beat, transformers at certain scales, especially on dense data like language.
Absolutely. Mamba 1 proved the potential. Its selective mechanism was clever, allowing it to focus on relevant information, and it performed well, particularly when given larger state sizes to work with.
It really felt like a signpost towards more efficient sequence models, maybe moving beyond just transformers.
Definitely. But despite its strengths, Mamba 1 ran into a practical hurdle, especially when people tried to scale it up for really large foundation models.
Which was?
Its primary computational method was inherently recurrent, step by step. Now, that's actually pretty efficient for inference when you're generating text one token at a time. You update the state, get the next token, update again.
Right, makes sense for generation.
But for training, especially large-scale training, modern hardware GPUs, TPUs, they thrive on massive parallel computations. They're designed for crunching huge matrices all at once.
Like how transformers and CNNs work.
Exactly. They saturate those specialized matrix math units. Mamba 1's recurrent nature, while enabling its selectivity, meant it couldn't fully exploit that massive parallelism. It was more sequential.
So it wasn't using the hardware to its full potential during training.
Pretty much. It required careful hardware-aware code, but fundamentally, it wasn't speaking the native language of matrix multiplication that these accelerators are optimized for. This created a bottleneck, a hardware efficiency bottleneck, specifically during training.
Okay, like having a race car stuck in city traffic, as you put it earlier. You can't use its speed.
That's a good analogy. Great potential, but limited by the operational context of large-scale training hardware.
All right, so Mamba 1, powerful, selective SSM, great for inference, but hit that training efficiency wall due to its recurrent computation not mapping perfectly onto parallel hardware. That perfectly sets up Mamba 2. You said the key idea here is structured state space duality, SSD, and you framed it as a fundamental rethinking, suggesting some SSMs can be seen as a type of causal linear attention. That sounds, well, almost paradoxical. How can a state-based model be like attention?
It does sound counterintuitive at first, doesn't it? But that's the power of this duality. Think about how we usually conceptualize these models. SSMs, we think recurrent, compressing history into a state. Sort of like our own memory finite, a bit fuzzy, processing things as they come.
Okay, the state carries the history.
Right. Transformers, on the other hand, are often thought of more like databases, They cache everything, every input token, and then attention lets them look back explicitly and in parallel across that entire stored history.
Explicit recall versus compressed state.
Exactly. Now, SSD reveals something quite remarkable. Certain SSMs actually possess both forms. They have an SSM-like linear recurrent form, the step-by-step processing, but they also have an equivalent attention-like quadratic form, a way to express the computation as if it were looking across the sequence more globally, albeit in a structured way.
Both. So it's not one or the other, but two sides of the same coin.
Precisely. Specifically, the paper shows that a particular kind of SSM1, where the A matrix, the state transition matrix, has a simple scalar identity structure, is mathematically dual to a form of structured masked attention that uses something called a one semi-separable structure in its attention mask.
Okay, that's specific. So a specific SSM type maps perfectly to a specific structured attention type.
Yes. Think of it like discovering that a complex melody played sequentially, the recurrent SSM, can also be represented as a single, intricate chord capturing all the harmonic relationships simultaneously. The attention-like form. SSD shows these SSMs have both representations available.
And why is that useful? Does it just mean we can think about it differently?
It's much more than just a conceptual shift. It means we can compute it differently. We can choose the computational path, the linear recurrent one or the quadratic attention-like one, based on what's most efficient for the hardware and the task, especially during training. That's the game changer. It unlocks hardware efficiency.
Okay, that makes sense. A choice of computational view unlocks efficiency. You mentioned the mathematical underpinning involves semi-separable matrices. What are those exactly, and how do they enable this efficiency?
Right, the math here relies heavily on these semi-separable matrices. You'll also see them called 1SS matrices, or SSS, sequentially semi-separable. The names themselves hint at the connection. Think about a standard matrix representing all pairwise interactions in a sequence of length t. That's a t by t matrix, right? It needs OT2, t-squared parameters, or storage. It grows quadratically.
Which is the problem with long sequences and standard attention.
Exactly. Semi-separable matrices are different. They have a special structure that allows them to be represented or compressed using only OT, linear parameters for the same sequence length t.
Linear versus quadratic. That's a huge difference for long sequences.
A massive difference. It's like instead of storing every pixel of a huge image, dense matrix, you store a compressed representation, like the key brushstrokes and how they connect sequentially, semi-separable matrix, much more compact. And crucially, you can perform computations directly on this compressed form using fast algorithms. You don't need to blow it up into the full t-squared matrix first. One key operation here is called comprod-sum cumulative product sum. It's a way to efficiently calculate running products and sums across the sequence, capturing dependencies without that quadratic cost.
So these matrices have built-in structure that allows for efficient, linear time operations capturing sequence dependencies.
That's the essence of it. They are the mathematical engine driving the efficiency of SSMs like Mamba 2.
Okay, so if SSMs are built on these efficient semi-separable matrices, what does that imply for how we compute the model's output, the forward pass? You said any computation method is like a matrix multiplication algorithm on these structures.
You've got it. That's the core computational insight from SSD. Any way you choose to calculate the output of the SSM, whether it's the step-by-step recurrent update or some other method, can be mathematically viewed as a specific algorithm for multiplying by this underlying structured semi-separable matrix.
And the dual modes you mentioned, the linear and quadratic forms, how do they map onto these matrix algorithms?
They map directly. The linear recurrent SSM form corresponds to using one of those fast lineotime algorithms designed specifically for semi-separable matrix multiplication. It operates on the compressed representation, step-by-step, very memory efficient. That's essentially what Mamba 1 did.
Okay, the traditional SSM computation.
Right. The quadratic attention-like form conceptually corresponds to what you'd get if you did expand the semi-separable matrix into its full dense t by t form and then did a standard matrix multiplication. Naively, that sounds slow, quadratic again.
But didn't we want to avoid quadratic?
Yes. And here's the clever part of Mamba 2. By recognizing the duality and the underlying structure, it can compute this quadratic form in a highly optimized way. It doesn't actually materialize the giant dense matrix. Instead, it maps the computation onto operations that modern hardware loves. Large parallel matrix multiplications, often using highly optimized routines called GenMs, general matrix multiply.
So it leverages the GPU's strength in matrix math even for the quadratic view.
Precisely. It might involve more total operations theoretically, but because those operations are massively parallelizable and map perfectly to the tensor cores on GPUs, it runs much, much faster in practice during training. Mamba 2 gets the flexibility to choose the compute path that best utilizes the hardware, overcoming Mamba 1's training bottleneck. And building right on that idea, viewing SSM computations as structured matrix operations leads us to the matrix mixer framework. This is presented as a really powerful, unifying way to think about sequence models. The basic idea is simple. View any transformation that takes an input sequence X and produces an output sequence Y, so Y is A theta, as a matrix multiplication. Y equals mx. Here, m is the mixer matrix, and its values depend on the model's parameters, beta.
Okay, y equals mx. That sounds very general. Transformers fit this view easily, right? M is just the attention matrix.
Exactly, transformers fit naturally. But the framework explicitly extends this view to other models too, like RNNs, and crucially for us, SSMs. It provides a common language, a common mathematical lens to understand and compare these different architectures.
So it's less about seeing them as totally separate species of models and more as variations within this larger matrix mixer family.
That's a great way to put it. It helps us analyze their properties systematically. What kind of structure does the M matrix have for an RNN versus an SSM versus a transformer? How does that structure affect its computational costs, its inductive biases, its ability to handle long sequences? It shifts model design towards a more principled engineering approach.
Makes sense. You mentioned the framework defines the sequence transformation on X and Y and RT. T is sequence length. What about P? You said it's like an attention head dimension. How does that work for SSMs?
Right, P is important for generalization. T is time or sequence length. P is like the feature dimension at each time step. You can think of it exactly like the head dimension in multi-head attention. A basic SSM might operate on P1, just a single channel or feature. But the matrix mixer framework easily generalizes this. You can apply the SSM operation across P1 dimensions, essentially treating the input as P-independent sequences or heads. You just broadcast the SSM parameters and operations across that P dimension.
Ah, so multi-head SSMs, analogous to multi-head attention.
Exactly. Parameters can be shared across these heads or kept separate. It allows for richer representations and often better hardware utilization, similar to why multi-head attention is effective in transformers. It makes SSMs more flexible for complex, high-dimensional data.
Okay. Now, connecting this back to SSD and attention, standard attention gets its power, but also its quadratic cost, partly from the softmax function, right? Does Mamba 2's SSD use softmax? If not, how does it achieve that selective attention-like behavior?
That's a key point. No, Mamba 2's SSD doesn't use the standard softmax activation. Dropping softmax is crucial for avoiding that inherent quadratic complexity. Softmax forces every token to explicitly attend to every other token, creating that dense interaction matrix.
So how does it work instead? What replaces softmax?
It borrows a technique from the linear attention literature. Instead of softmax, it uses a kernel feature map. Essentially, you transform the query and key vectors into a different space where their simple dot product approximates the effect of the softmax weighted sum. This allows the main computation to scale linearly with sequence length.
Okay, so a kernel trick avoids the softmax cost. But how does it get the structure? Isn't attention just about similarity?
Good question. That's where the structured part of SSD comes in. After computing the logis using this kernel approach, SSD multiplies that result by an input-dependent one semi-separable mask. Remember those semi-separable matrices?
Yes, the efficiently structured ones.
Right. This mask, derived from the input and having that efficient structure, is what introduces the selective, context-dependent weighting that mimics attention's ability to focus, but it does so with linear complexity. It's the combination of the linear attention kernel trick and the structured semi-separable mask that gives Mamba 2 its power and efficiency within the matrix mixer framework. So we've talked about the theory SSD, the matrix mixer view, but does it actually work better in practice? The answer is a resounding yes. The reframing directly leads to significant practical wins, tackling that Mamba 1 training bottleneck. Firstly, faster algorithms. Because SSD allows computation via hardware-friendly matrix multiplications, those gems we mentioned, the algorithms are just much faster than Mamba 1's selective scan, especially during training.
Faster because they use the GPU tensor cores more effectively?
Exactly. The computation becomes dominated by these highly optimized, dense matrix operations, rather than sequential loops that are harder to parallelize efficiently. This means much better hardware utilization, faster training iterations, and better scaling to larger state dimensions, the N parameter in SSMs. We're finally letting the hardware do what it does best.
And that improved hardware mapping unlocks something else huge, right? You mentioned transferring systems optimizations from the transformer world. That sounds incredibly valuable. How does that work for things like distributing training across many GPUs?
Yes, this is a massive practical advantage. Let's talk sequence parallelism, SFT. This is when you have sequences so long they don't fit on one GPU, so you split the sequence itself across devices. Mamba 2 adopts a very similar block structure to Transformer's residual connections, normalization layers in the same places.
Mhm.
Because of this structural similarity, established SP techniques like using reduced scatter and all-gather communication patterns for the non-core parts of the block can be applied almost directly.
So you don't have to reinvent the wheel for distributing the standard parts of the network block.
Precisely. It inherits years of engineering effort poured into scaling transformers.
Okay, that covers the standard block components. What about distributing the core SSM SSD computation itself, the part that processes the sequence context, sometimes called context parallelism?
Good question. For that core computation, the SSD framework's connection to structured matrices helps again. The sequence can be broken into chunks or blocks. Each GPU computes the output and the final state for its chunk. Then, only the state needs to be passed to the next GPU in the sequence chain, using simple send-receive operations.
So you compute locally, pass a compressed state, and the next GPU picks up from there.
Exactly. It maintains the sequential dependency across the distributed system efficiently, without needing every GPU to see the whole sequence or communicate excessively. It leverages the block-structured nature inherent in the SSD formulation.
Very clever. What about another common headache? Batches with sequences at different lengths. Transformers usually pad them, which wastes compute. How does Mamba 2 handle variable lengths?
This is another area where SSMs inherently have an advantage, and Mamba 2 implements it elegantly. Instead of padding, you can just concatenate all the sequences in a batch into one long sequence.
But then how do you prevent information from leaking between sequences in the batch?
That's the trick. At the boundary token, the last token of each actual sequence within that long concatenated sequence, Mamba 2 simply sets the state transition matrix at to 0 for that step.
Setting at to 0, what does that do?
It effectively breaks the state propagation. If at is 0, the state from the previous token, the end of one sequence, doesn't influence the state computation for the current token, which would be the start of the next sequence in the batch. It resets the state implicitly, without needing any padding tokens or complex masking.
Wow, that's neat. Just zeroing out one parameter prevents state leakage between packed sequences. Much more efficient than padding.
Much more efficient. Saves compute, avoids potential issues with padding tokens influencing results. It's a cleaner solution for real-world, messy data.
Okay, the systems and efficiency gains sound substantial. But the proof is in the pudding, as they say. What about actual performance? Did Mamba 2 show improvements on tasks, synthetic benchmarks, language modeling? And what about those hybrid models mixing Mamba and attention?
The empirical results are definitely strong and validate the approach. On synthetic tasks designed to test long-range memory, like multi-query associative recall, MQAR, Mamba 2 shows clear improvements over Mamba 1, even when controlling for the state size.
MQAR tests retrieving specific facts from context, right?
Yes, it's a good proxy for memorization capacity. And importantly, increasing the state size, N, in Mamba 2 consistently boosts MQAR performance significantly. Going from N16 to N64 or N256 allows it to store and recall much more information, confirming the state is being used effectively. On standard language modeling benchmarks and downstream tasks, Mamba 2 holds its own against strong open-source models like Pythia and RWKV4 at similar scales, often showing advantages as context length increases thanks to its linear scaling.
So competitive performance on standard tasks. What about the hybrids? That seems like a really interesting direction.
The hybrids are indeed very promising. Models like Damba and Zamba explicitly combine Mamba 2 SSD blocks with standard transformer attention blocks. For instance, a Jamba model with mostly Mamba 2 blocks but a few strategically placed attention blocks outperformed both pure transformer and pure Mamba 2 models of similar size, around 2.7B parameters, trained on a large dataset, 300B tokens.
So combining them is better than either one alone.
At that scale and configuration, yes. The research suggests interleaving the Mamba 2 layers uniformly seems to work well. It points towards a synergy Mamba 2 handling the long-range, fine-grained compression efficiently, and attention providing the powerful, explicit global context mixing where needed. Best of both worlds.
Fascinating. Were there any other specific tweaks to the Mamba 2 architecture itself beyond SSD that helped achieve this performance and stability?
Yes. A couple of notable refinements. One is orthogonalizing the sequential projections within the Mamba block. Mathematically, it helps ensure different parts of the state update are more independent. This improves numerical stability during deep training and also seems to help with tensor parallelism, distributing the computation within a single block across devices. They also added an extra normalization layer. While it gives a small, direct performance bump, the main reported benefit, especially at larger scales, was improved training stability. These aren't headline features like SSD, but they're important engineering details for making large models train reliably.
And one last practical point. Knowledge distillation. Can Mamba 2 learn from giant pre-trained transformers?
Absolutely. This is another compelling practical angle. Frameworks like Mohawk have been used to distill knowledge from large pre-trained transformers into smaller subquadratic models like Mamba, which uses Mamba 2.
So the Mamba model learns to mimic the transformer.
Essentially, yes. It learns the input-output behavior of the larger teacher model. And because the SSD matrix structure in Mamba 2 provides a surprisingly good approximation to the transformer's self-attention matrix mixer, this distillation process works particularly well. The Mamba student can effectively capture much of the teacher's knowledge,
allowing you to get transformer-level performance in a more efficient Mamba architecture without the full pre-training costs.
Exactly. You leverage the massive pre-training compute already spent on the transformer, but end up with a faster, more efficient model for inference and fine-tuning. It's a very practical way to create powerful yet efficient models. #TagGemi. The broader implications of SSM attention duality.
Stepping back a bit, the implications here feel quite profound. This structured state space duality, finding a deep mathematical link between SSMs and attention, it suggests the lines we've drawn between these architectures might be more blurred than we thought.
I think that's exactly right. It challenges the traditional view of these as fundamentally separate families. Maybe recurrent state compressing and parallel memory heavy are just two different ways of looking at and computing solutions to the same underlying sequence transformation problem.
Like different coordinate systems for the same space.
Perhaps. Or different algorithms optimized for different aspects of the same underlying mathematical structure. This duality also highlights where SSMs have unique strengths. They really excel with raw, fine-grained, potentially untokenized data think, character-level text, raw audio waveforms, DNA sequences.
Why is that?
Attention often relies on having meaningful tokens as input. SSMs, with their continuous time formulation and state compression, seem better suited to processing these dense, high-resolution streams and compressing them into useful representations. We see this in architectures like HNets, where Mamba 2 layers are explicitly used in encoders-decoders because of this strong inductive bias for compression. They're good at finding structure in raw data.
And does this unifying view, especially the matrix mixer framework, help us design new models in a more principled way?
Definitely. If you view sequence modeling as designing structured matrix mixers, the M and YMX, you can start asking, what mathematical properties should my M matrix have for a given task? For example, if you need bidirectional context, like in mass language modeling, maybe a semi-separable structure isn't quite right. The work on Hydra, a bidirectional Mamba relative, took exactly this approach. They designed it using a quasi-separable matrix structure, which is mathematically suited for non-causal interactions.
So they chose the matrix structure to fit the task's requirements.
Precisely. Hydra, built on this quasi-separable matrix mixer idea, performs exceptionally well on non-causal tasks. It shows how the framework enables systematic design, moving beyond just adapting existing architectures.
So this whole deep dive really paints a picture of a converging landscape. Not separate islands of transformers, RNNs, and SSMs, but maybe a continuum, unified by these deeper mathematical frameworks like SSD and matrix mixers.
I think that's the emerging picture. Attention and recurrence might just be different computational strategies, different views onto the same fundamental operations chosen based on hardware, data, or task needs.
It offers a much richer toolkit for building future AI systems.
Absolutely. We're moving beyond a single dominant architecture towards a more nuanced understanding, allowing us to combine strengths and design more tailored solutions.
Which leads to a fascinating final thought for you, our listener. If this long-standing divide between memory-heavy transformers and state-compressing SSMs is partly just a matter of computational perspective, as SSD suggests, what happens next? What entirely new kinds of hybrid architectures might emerge when we truly embrace this shared mathematical foundation, perhaps blurring the lines even further and creating models with capabilities we haven't even conceived of yet?
That's the multi-billion token question, isn't it? We really encourage you to think about how this deeper, unified understanding could impact your own work. How can we leverage this duality, this matrix mixer perspective, to build the next generation of AI models that are more efficient, more versatile, and ultimately more intelligent? The path forward looks incredibly exciting. Thanks for joining us for this deep dive.